smart buildings. We work a lot with data and bring all that together. So it's architectural, electrical, mechanical. We all have that in our home, in-house. We're specialists in the larger utilitarian projects. Some of the projects will be part of this presentation, so you will know them probably, I think. And yeah, our hearts beat faster from renovation and sustainability projects. So not the greenfield situation, but the complex renovation situation. So in that way, we are a central player in the built environment. I wanted to start with that because SPIE is not that well known right now. But now let's switch to who we are. My name is Bas Woltman. I'm a design and build manager. My background lies in architecture. I've studied at Delft, not in Eindhoven. There's some moments in my life that I thought I would rather have studied in Eindhoven than in Delft, to be honest. But it's a whole different discussion. I was an architect from 2007 till 2013. But now, after working for Heijmans and now Strukton, which is now SPIE, I'm responsible for the integral projects as a design manager. And at SPIE, I'm a design and build manager, which means I'm responsible for projects from beginning till end. Two of my recent projects are the temporary housing for the Tweede Kamer, the government of the Netherlands in The Hague. That was a big project of mine. And a recent project which I'm still working on is the Dutch National Bank, the Nederlandse Bank in Amsterdam. So that's who I am.
And I am Mike. I studied here in Eindhoven in 2010. And my mission is to improve the performance of buildings, which I do for the Van Gogh Museum, TNO, and I work on the Brainful Building subsidy project as well. More on that later.
Yeah, we split our presentation in two parts. First, a more general part about the design and build phase, and Mike will go further into a more specialistic part, which is to do with data after we finish a building. And the main case we want to make is that digitization is the main issue towards the next step in sustainable building management. I'm saying building management because it's the whole process. It's not only the design phase, it's not only the building phase, construction phase, but it's also the maintenance phase after that. We are moving from a situation that was a lot of paper. When I started my studies in 2001, I even had a tekentafel, so I was working on paper. And only in the second year we started really using digital products for design. But now, yeah, we are moving to a world where it's not only a digital drawing, it's much more information, much more data. And it's sometimes even overwhelming. We produce a lot of data in this chain of corporations and designers, and we are all using it in a different way. And we think the key lies into managing that in the right way so that we can make the next step. Because having all this data is one thing, but truly utilizing the data, that's a whole other thing. Depends on how you structure the data, which phase, which detail level you have in every phase. The accuracy, we see a lot of faults in accuracy in projects, so that's a big issue. And Mike's main point will be the manipulation of that data and to do simulations with it. That's what today is all about. First, let's start with the design and build phase. My main issue in my work. What we see a lot is that although we think we do speak the same language, we do not speak the same language at all. There's a lot of differences that arise during the whole process. What we see is a client says he wants something. He specifies that in a program and it's already something else. An architect interprets that and it's again even more different. Then we as contractors start to build it and no, we have a lot of fights about it, so probably we'll build something different than the architect eventually wanted. Then when we deliver the building, it performs differently, but as the client didn't even specify what he needed. He specified it only what he wants. So there's a big difference between A and F. There's a big mismatch. So that's an important thing we have to do in this chain. And what we see, probably a figure that all of you know, I think Le Corbusier was the first to draw it, the influence line which you have in a building process, and the cost of changing something in that whole process. They get contradictory in the longer you go into the project. And what we really are focusing on, and I think you are focusing it here also on the BIM side of things, to make it really intelligent so that we can do all the changes we want to do. We do the first time right principle. So we're shifting all the effort to the front. That means that, well, historically our main business was building. Now we want to control the design phase, because that's where the differences are made. And what we see is that we have to be really careful to have the development of the data in a detail level that's fit for the phase. So not too much, but also not too low. And a big thing in recent years is, of course, the circular opportunities. We do a lot of renovation projects. And what we see is that we are wasting a lot of circular chances. So we're throwing away a lot of money, to say like that. So it's very important for us to know what is already there, to know what is the condition of what we're working with, and to know the value of what we're working with. And an important thing is how to dismantle it. So that's for what we reuse and also what we create. Those are the main things we are working on. I started with documents. 3D was something of a year or 5 back. It was interesting to know things 3D. But now we are way further. We are working on a linked phase. So how are we going to go to step 3, even to an integrated phase where we integrally use data, where a designer creates data that we use to build, which we use to maintain afterwards. So we wanted to just show a few cases of what we are running into in our jobs and how we work with that. The first case is what I started before. What does the client really want? What we see in projects, it started with the PPS projects where output specifications were made. That there was no structure in it, and what we see now is that a lot of clients write a program of demands, but also try to create already a design, and it creates a sort of situation where they say it's both your contract, the program of demands you have to make, the design you have to make, and when they're contradictory, the sort of cherry picking situation arises. So what we are trying to do now is to go to a world where we're no longer writing PDF Bibles, PDF Bibles, program of demands, bestekken, all that kind of stuff. Just try to make a real integral system in which we can put every demand on the right level, on rooms, on elements, so that we really know what we're going to make. That's one of our main things we're focusing on. And we're doing that with Relatix. I think many of you know Relatix, but that's a program in which we use to make all the different verifications and validations of all the steps we do in the projects. Then a second case, that is, we do a lot of renovation projects. This is one of my recent projects. Now we're going to the more visual stuff. This is the Nederlandse Bank, the Dutch National Bank. They have a renovation in the center of Amsterdam, and we do that for them at this moment. This is a picture from, I think, 2 weeks back. So we're completely renovating the facade and repurposing parts of the building. But what we run into is that hardly any client really knows their building. So how to get a grip on what is already there, how to influence the design phase with what is there, that's a big issue. A lot of revisions are lost. Because in the end we want to create this. This is an image from Meccano. Meccano is the architect of the building. We want to bring back the luster it had in the years before. It was designed by Danger, which it was built in 1968. And it had a lot of modern and really nice influences, but now it's a rundown building, so it needs a good work. This was the old quality. When we came there, it was completely filled in. floors everywhere, offices everywhere. So this was completely gone. And eventually it's supposed to be the same again in the new situation. So there's a lot of work we need to do there. This is one example. On the left side, you see the end result where the whole safe, I must say, the kluis. I don't know if that's the vault maybe in English. It's supposed to be completely visible. In the beginning, there was only offices all around, so you couldn't see it. There was floors there, so you couldn't see the whole safe. And what we in the end up with is completely open. We saw it. We removed all the floors in between. So that's a really big construction project. And when we started, we noticed that the archives are never complete. The client already made a BIM model, but that's also a risk because the BIM model implies a sort of level of detail and a level of knowledge. And everybody starts to work from that. The architects started working from that BIM model, and it was sort of the truth. And now, after we stripped it away, the building, it appeared it was completely different. So there's a few examples I wanted to share. For instance, nobody is taking note of what's happening over the years. We didn't do any of these infills, but we have to do really big structural changes in this building. And nobody knew these holes were even there. So the complete design phase was redone in late stages. And another example is nobody knew this was there. There was probably in the beginning, the column was a little bit more to the right. And just to remove this column and to place it a little bit more to the left, they made this structure, which was not visible in the BIM model, but it was the main point in which the installations came out of the shaft. So complete redesign was necessary on this stage. So what we're going to do now, what we are doing in this project, for the first time real intensively, is the 3D scanning. Completely scanning the entire interior and then using strategic decisions on whether if it's 1 centimeter off, it doesn't matter, of course. But when it's more off, then we try to incorporate that into the 3D model. And this is an example. This is the floor. It's hardly you can hardly read it, but there's 4 centimeters difference between the outer edge of the floor and the lowest point of the floor. And we had to make new cable ways in the floor for the workplaces. So that was a real big difference. And without 3D scanning, we couldn't get any grip on this. So this helped us really to redesign the position of those gutters in the floor and make it work, because the whole building was, it's even 65 millimeters shorter than it should be. And something really new we did was the circularity win. So what you see here is 2 main towers. The square tower is original. The round tower was there only from 1991, I think. And we completely reused this building because we could scan it. We could understand completely how it was built up and how we could strip it again. And this is the situation where the building is right now. It's completely inside in large warehouses. All the floors, all the facade elements, everything is there, and we will build it. Someone else will build it somewhere else in Amsterdam in a new function. We also have circular chances in the building itself when we reuse, for instance, wood. The panels that's going in the crane there on the right image, the infill in wood was completely found. One of our people working for us came inside and he said, "I found a lot of wood. I found a lot of wood. What can we do with that?" And so we reused it. And now we're working with CB23 to have a way of calculating the impact we make with all these initiatives. And try to influence the way that we develop a NAN for circular measurement, and to have influence on how that works and how regelgeving. Sorry, my English is not that easy. How to incorporate the way we measure the impact of circularity into the regulations for the future. Of course, we also have design collaboration, in which we use 3D models to combine the different elements we are designing. So a lot of work goes into this kind of systems in which we compare each other's work and clash them onto each other. Then the last case I have is the one where we take it outside. One of the main developments we have right now is to use systems to take the models outside and to have this kind of representations in which we can see what needs to be built, not only on 2D graphs but also in 3D. Also allowing us to mark which different faults there are, which need to be corrected on the site itself. Digital, I don't know the word for that. Digital measuring for taking where holes need to be made and stuff like that. That's also a big step. And what we now notice is that it's very slow. So every time we want to have a new insight into the building, it takes a few days. And the future is I think is like this, where we can have these kind of robots that just in the evening or in the night walk through the building and scan the whole 3D situation. But this is the next step. We're not there yet. Then we'll make a small bridge to the story of Mike. The results are just the beginning. So in the end, we get proud from this kind of results. This is the temporary housing for the Tweede Kamer. For me, it's the sort of endpoint, but for our organization, it's sometimes even the beginning. After this, we start the phase of maintenance, and then the really smart stuff starts. So, Mike.
Yeah, so the building is built, and then we're starting to maintain and operate the building for a few decades, right, before we start renovating it again. And I will tell something more about how we can use data in this operating and maintaining of a building. So smart building operations ensures higher levels of comfort, lower energy consumptions, higher availability of critical installations, lower cost of total ownership, and insight in compliance. And I hear you thinking, sure, but how? So that is where I will focus on in this presentation. I will tell you how we use data to achieve higher levels of comfort, lower energy consumptions, higher availability, lower total cost of ownership, and insight in compliance. And we do this with Pulse Core, which is the monitoring platform that Sphere is using, where we give insight into the building's performance to our clients, but also do analysis in there. Here are some of our clients. So Van Gogh Museum is one of our clients, which is connected to Pulse Core, as well as the Muziekkwartier Enschede, the High-Tech Campus, PGGM, Hogeschool Utrecht, and Rechtskantoor de Knoop. But actually there are more than 750 buildings connected to Pulse, where we're constantly monitoring the performance of the buildings. Pulse has been 10 years in development, with more than 50 specialists and consultants, 250 strategical clients, 110,000 sensors which are actively monitoring the buildings around the Netherlands, with a data lake of more than 60 billion values. So Pulse Core uses information that comes from the building management system, maintenance data, energy data from the energy companies, and sensor data. So for the building management system, we can talk to Priva, Souter, Honeywell, Siemens, Johnson Controls. For maintenance data with SAP and Focus. With energy data, the main energy companies we can use the data of. Of course, we can use data of KNMI, as well as IoT Spot, where you can do room reservations. Sensor data, where you have wireless sensors placed in the room, so you can see the performance of the rooms or the actual indoor climate of the rooms. And all of this data is gathered to get insight in the building performance and possible enhancements. And this is where a problem arises. There was a study published in 2016 where it appeared that data scientists spent roughly 60% of the time on structuring the data. And if you think about this, if you have a technical room and installation, how would you call a sensor like this? You have to give it a name, right? So you can use it in your analysis. But if you know the name for this sensor, how would you call all the other sensors? And you have to be very strict about this, because if you have it for one building and you have 750 buildings in your in which you have to maintain and operate, you have to be smart about how you call these sensors so you can reuse the algorithms you're writing. This is another example. Here you see the amount of sensors that are present in the air handling unit. So you see there are a lot of sensors present, and we have to be strict about how we name these different sensors. We are starting to use the project Haystack, where a sensor like the temperature of the discharge air, we give it the tag discharge air temperature sensor. So we all know this is the sensor name. So in Pulse Core we try to structure this data in an efficient way. So coming back to this higher, lower, insight and compliance. So how do we actually do that? And so far I told you, well, we're using a monitoring platform and we are doing something smart with data to reuse this data. But now comes the fun part, actually using this data. And we have several functionalities in Pulse. One of them is real-time adaptation. Look at an air handling unit. This is a typical one where you have the air from the outside, where returned air as well, goes through a filter, a heating battery and a cooling battery, and then through the ventilator, and it is discharged into the rooms. What if a belt breaks here, a belt rupture? Then an alarm is sent by the building management system towards the Pulse operators, which are constantly monitoring the building stock we are maintaining. They can, from a distance, remotely access the building to see what's really going on, and from there on dispatch the engineers in the field, so they can prepare this belt again. Some other functionalities like sustainability and comfort. This is one of the typical graphs you can make with the monitoring platform, where you see the daily trends. So you can see, well, every day we have a peak and a lower, and peak and a lower. And for instance, during the weekend you expect that for a normal office, you expect that there's no energy demand, or actually there's a lower energy demand. So here's nothing really wrong. You can look at different things, so you see different alerts arising where the inlet temperature was not the one it was set. So there's an indication for a fault. And so this is a trigger. It's not really that's really something wrong at the moment, and an engineer has to go there, but it's an indication that something can be optimized there. You can look at indoor comfort with the adaptive temperature limits, where on the horizontal axis you have the running outdoor temperature, and on the vertical axis the indoor temperature. And you have sort of a regulation, and you can see if it's indeed comfortable inside or not. Some other functionalities are, for instance, optimization. And here I'm going to use one of the examples. This is a real case, but I have to I cannot tell who the client is here. But there was a large building with a chiller, a boiler, a cooling tower, as well as some air handling units. And this was the basic idea. We have the chiller, we use the chilled side, the cold water always. But this idea and the design process came that we could reuse the condenser side as well. So we could use the heat that is produced by the chiller for some final conditioning of the air handling units. And then it was thought, well, maybe this is not enough all the time. So probably we should use a boiler as well. And maybe if none of the heat is used in the air handling units, then we need a cooling tower as well to dispatch the heat if none of the air handling units really needs it. So that was the idea. And then the design idea was, well, we use neither A or B, so nor A nor B, so because all the heat is used in the air handling units, or we use only A or only B. That's the design idea. And now the control strategy was very simple. So when one of these valves was opened for more than 80%, then the boiler kicks in, and would regulate the temperature to 60 degrees. And this was the design, and this was what was actually built. So you see a large difference in the capacities of the different air handling units. including one very small one compared to the other one. The smallest one was roughly 10 times smaller than the biggest one. And this was what was occurring. You see this, the valve opening of the small air handling unit rapidly opening and closing. It was a small air handling unit with a system behind it with a very large capacity. So as soon as it opened, it directly closed again. Also meaning that there was a lot of heat still present inside the system, which then had to be dispatched by the cooling tower. So this design idea was basically a great idea. Well, let's reuse the heat from the chiller, but in reality, something was built that didn't work anymore, because this was what happened. Constantly, the boiler kicks in, and it was cooled down again by the cooling tower. And if you then, you change the control strategy. Actually, it was one set point, and by the changing of one set point, we stabilized this installation. Some indication of what is saved by just changing one set point in this installation. It was roughly 0.3 gigawatts hour, which is roughly the same as 22 houses, just by changing one setting in the building management system. And that doesn't include that the indoor climate became more stable by this. Maintenance decreased because all of these valves were opening and closing all the time, which is now not occurring anymore, so there's less maintenance. And we didn't include that the energy was needed for the cooling tower. But just as an indication what you can do after the building is built in the operating and maintaining phase. Something about fault detection. Let's say you have to say something about energy use of a building, and you get this graph, and someone asks you, well, is this a good graph? Is the energy performance of this building, is that okay? It would be great if you get some type of comparison. And what we do at Pulse is we train a neural network or a machine learning tool to predict the energy use of a building. So given the weather condition, given the amount of people that are in the room, which you can count with sensors which you place near the entrance, with 2 beams where you can count the people that are coming in, so you know the amount of people that are in the room. Of course, you know the weather conditions, and we also track the elevator movements, so you quite well know where the people in the building are. And then you can make a prediction of how much energy you expect to use for a building. And here you see, well, these 2 lines are quite comparable to each other. However, in this case, you see that there's quite a big difference between the two. The reality and the prediction of the model were quite big. So this is an indication that something is going wrong. And that's great, right? To tell something that something is going wrong. But it's only a first step. You want to know what is going wrong, so you know where to look at. And that's something that is that's called diagnosis, and something that's under development now, for instance, in the Brains for Buildings research project. And look at something completely different. So I'm not a doctor in any way, but let's say you have a fever and you are coughing. Well, then there's a high chance you have the flu. Let's say you have the fever and you're coughing, but you're also quite tired and you have less taste. Well, maybe it's quite likely that you're having COVID instead of just having a regular flu. The same ideas can be applied to air handling units, where if the inlet temperature is the same as it's set to, then it's okay. But let's say the inlet temperature is different than you want. And also you see that the supply temperatures were in line, then probably there's something wrong with one of the valves. If you have the same conditions, but there's also extreme weather and there are many people present in the building, maybe it was more like a limited capacity by design. So it's not really a fault, it's just a limitation that's set in the design phase. Or maybe you see a lot of pendelgedrag, so a lot of turning off and on, so rapid switching of the status of the installation. Well, that's probably a poor control strategy. So instead of using just looking at this data can be quite complicated, but by the use of Pulse, you can go directly to what is going on. So the left graph, you see, well, a lot of graphs, but on the right side, where you have done this analysis and shows, well, there's a high chance that there is a poor control strategy in this HVAC system. Done something about predictive maintenance. We have a sensor which we can place on elevators, where we can track the movements of all the elevators in a building. And in the graph you see there's on the horizontal axis you see the time, and on the vertical axis you see the amount of movements that the elevator makes. And you can see that it increases rapidly, and then suddenly there's a slight decrease in the slope. That was when COVID hit, and you see that Pulse then, or the monitoring platform then recalculates the moment that maintenance is needed. So based on this new use of the elevators, we predict, well, we can do the maintenance at a slightly later time because it's not used that much anymore. This is another example where with the green bar you can see the advised maintenance time, and here it was not followed up. So they ignored this advice, and you can see with the gray lines that a lot of errors occurred when this advice was not followed. Something else for predictive maintenance is the filters in air handling units, which have to be replaced regularly. Over time they get polluted, and then when they are polluted you need to change the filters in air handling units. You can, by measuring the pressure drop over a filter, you can determine when it's time to replace it. But you can also predict it. Of course, this is no longer a linear relationship, but by an exponential relationship you can determine when it is expected that you need to change these filters. Then something about forecasting. Remember this model that I talked about earlier, where you can use an artificial intelligence or machine learning model to predict the energy use of a building. The same model can be used to forecast the energy use of a building, where you not feed it with the actual weather conditions, but with the weather forecast. And also you know the occupancy of last week, so you can feed it with the foreseen weather as well as the use of last week. So you can say, well, quite given the use of the building of last week and given the weather forecast, this is the expected energy use for a building. And this is all fine for to use for energy, but you can also use it for the cooling water temperature or the cooling capacities. And if a heat wave is starting to arrive and the cooling capacity is too limited for this, maybe you can start pre-cooling the building. You get an alarm bell, it's time to pre-cool your building, because otherwise tomorrow or in the day after you have a problem with overheating of the building. And maybe you can inform the building users. So going back to this question, right, where I stated, well, with data we can ensure higher levels of comfort, lower energy consumptions, higher availability, lower total cost of ownership, and insight in compliance. And I try to explain how we do this with Pulse. And I think we can do this with the smart tagging, so the smart use of the data, as well as these core functionalities like the real-time adaptation, the fault detection, as well as the diagnosis, and the weather forecasting. And then the last thing you have to do is really act on the findings. It's cool to find some things where improvements are possible, but we also have to implement these improvements. And with that, I would like to finish this presentation. Are there any questions? Yes.
What do you think are the things that really make companies like you guys harmonize with architecture? Are there certain aspects that really stand out?
I think because we can see the whole process from beginning to end, the collaboration needs to be started much earlier in the process. We each have our all expertises, but when we combine them, I think there's much better buildings that we can make. And a lot of our work has to do with installations and with the comfort inside a building, and they're completely different people in a company like ours, but there are also people that were formerly architects or understand how an architect speaks. And if you combine that, not by first making a design and then having someone else building it, then you can make real steps. And I think that's a process we are both learning. Architects are learning to work with us and we are learning to work with them, sometimes in construction teams, sometimes in design and build processes. But we are really getting there at this point. So I think the next years is going to be a real good development on that side. Is that an answer to your question?
So first of all, thank you to you guys to coming over here and give this wonderful lunch lecture. A little present for you. It's always struggling to give this. And